In this lesson, we're going to learn how to predict the three-dimensional structure of a molecule. So what we've learned so far is how to draw a molecule's Lewis structure, which is a two-dimensional representation. What you're going to learn how to do is how to analyze the Lewis structure to determine the actual three-dimensional structure the molecule takes. We'll use that information in a later kind of lesson to identify the polarity of the molecule, and then we'll take that information in another lesson and learn how to predict information about the intermolecular forces that molecules are going to interact with and their environment. All right, so molecules have a certain three-dimensional shape, and that shape is so important because it determines many of that molecule's chemical and physical properties. For example, your tongue has different taste buds. Those taste buds are able to perceive different taste based off of the shapes of different molecules. So for example, your sucrose, your sugar, your taste buds can perceive that what you're eating is sweet based off of the three-dimensional structure of that molecule. Your taste bud's able to send a message to your brain telling you that you're eating something sweet because of that three-dimensional structure of the molecule. All right, so what we're going to look at is two different ways to look at the geometry of a molecule. The first type that we'll look at is what's called electron domain geometry. Then the second type is what's called molecular geometry. So a molecule's electron domain geometry is the shape that is created by the way that the electron domains are arranged around a central atom. There's 5 different electron domain shapes: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. A key part of the lesson today is understanding what an electron domain is. So an electron domain is any place where you would find electrons around a particular atom that you're analyzing. So a non-bonding pair, a single bond, double bond, and a triple bond, they all count as being a single electron domain. What you're going to do is you're going to analyze a central atom to determine how many electron domains are around it. So if there are 2 electron domains, it's going to have a linear shape. You can see in these images, the orange kind of sphere would represent the central atom, and those purple things would represent the electron domains arranged around that central atom. If there's 3 electron domains, it's going to be trigonal planar, 4 would be tetrahedral, 5 would be trigonal bipyramidal, and then 6 would be octahedral. So now let's go through and actually kind of analyze some molecules to figure out their electron domain geometries. So the first key thing is you have to have a correct Lewis structure. Then you're going to look at the central atom to determine the total number of electron domains. So remember, we're counting a single bond, double bond, triple bond, or a non-bonding pair as being a single electron domain. So when I'm looking at xenon tetrafluoride, it has 1, 2, 3, 4, 5, 6 electron domains around that central atom. Therefore, it takes on an octahedral electron domain geometry. So what I want you to do is go through and analyze these 2 molecules. You're analyzing the central atom, determine the total number of electron domains, then use the little table in the upper corner to determine what electron domain geometry that molecule would have. So for H2O, 1, 2, 3, 4 electron domains, it's going to be tetrahedral. For CO2, carbon has 1, 2 electron domains, so its electron domain geometry is going to be linear. All right, so now we need to look at the different types of molecular geometry shapes a molecule could take. So you can have linear, bent, trigonal planar, trigonal pyramidal, tetrahedral, seesaw, square planar, trigonal bipyramidal, or octahedral. So what the molecular geometry does is it just shows you the shape that is created by how the atoms are arranged around that central atom. Sometimes a molecule's electron domain geometry is the same thing as the molecular geometry, but other times they're going to be different. So the electron domain geometry is the shape that would be created by how all of the electron domains are arranged around that central atom, whereas the molecular geometry just looks at the shape that's created by how the different atoms end up having to be arranged around that central atom. To determine the molecular geometry, you first need to draw the Lewis structure. You then analyze the central atom to determine the 3-digit VSEPR number. Then you use the VSEPR chart to determine the molecular geometry shape. So the 3-digit VSEPR number, the first number is going to be the total number of electron domains. So the number of non-bonding pairs, single bonds, double bonds, and triple bonds around that central atom. The second number is going to be the number of single, double, and triple bonds. And then the third number is going to be the total number of non-bonding pairs around that central atom. So if you take the second number and the third number and you add them together, they should equal the first number in the 3-digit code. All right, so what I want you to do is go through and identify what each number represents. So remember that first one is the total number of electron domains. So non-bonding pairs, single bonds, double bonds, triple bonds around that central atom. The second digit is going to be the number of single, double, and triple bonds. And then finally, that third one is just the number of non-bonding pairs around the central atom. All right, so let's kind of go through and look at two examples and how would we determine the VSEPR number for each one. So for that first example, xenon tetrafluoride, there's 1, 2, 3, 4, 5, 6 electron domains. So the first digit's a 6. For ozone, when I'm analyzing that central oxygen, there's 1, 2, 3 electron domains total. So 3 is the first digit. All right, so for the second number in the code, I'm just counting the number of single, double, and triple bonds. So 1, 2, 3, 4, 1, 2, so 2 is the second digit. And then for the third number, I'm counting the number of non-bonding pairs around the central atom. So 1, 2, 1. So now I have the 3-digit VSEPR number for each of these molecules. Then I would look at the VSEPR number chart in order to determine the molecular geometry. So 3, 2, 1, that corresponds to bent, whereas 6, 4, 2 is going to be square planar. What I want you to do is go through for this example, determine the VSEPR number, then state what the molecular geometry would be. So the number would be 330, that would be trigonal planar. And for this next one, same exact thing. What is the 3-digit VSEPR number, and then what would the molecular geometry be? So 550, and it would be trigonal bipyramidal. So when it's in the Lewis structure, you're not able to see what this actual shape looks like. You either have to use kind of a digital modeling tool or an actual physical modeling kit to see what these different 3-dimensional shapes look like.